Hello and welcome to our next class in computational finance. Last week we talked about the theory behind the capital asset pricing model, and we saw that in portfolio theory and portfolio optimization we are naturally led to optimization methods, and this is what we will be looking at today. We'll start with unconstrained optimization, that is optimization without constraints, in German Optimierung ohne Nebenbedingungen. We will look at some very classic methods, gradient-based methods, Newton methods, but also some heuristics that are derivative-free. And later on, we'll also have a look at optimization under constraints, where, for example, we have a budget constraint. We only have a certain amount of money that we can invest in our portfolio setting. Maybe we have an upper limit for our overall shortfall risk, or we have some other constraints that make sense in an economic setting. And we'll have a look at these very general methods for optimization with and without constraints. And then, at the very end, we'll also have a very large example for portfolio optimization in practice, where we'll see how we can actually employ all these methods in a setting where we have real empirical data for a portfolio of German stocks, and we'll try to optimize our portfolio. So we'll start with unconstrained optimization, and again, we'll do this in very general terms. Usually we will be looking for at least local optimum of a nonlinear function. If it's linear, we don't need optimization. So naturally we are looking at nonlinear functions here. And usually they are iterative. Iterative in the sense that you have one solution, and in the next step, you're repeating what you've done just now, trying to improve on the quality of your found solution, and you're trying to close in on the supposed local optimum. So we have a sequence x of k of approximate solutions, and this iteration sequence is required to converge against and converge to the solution we are looking for. So again, if you remember last week, we only need to look at minimization problems. Why? Because you can easily transform equivalently a minimization problem into a maximization problem and vice versa. So in order for the sequence, for the iteration sequence, the Iterationsfolge, to go into the correct direction of a local optimum, for each entry, for each entry in the sequence, xk, we first need to look for a descent direction. That is, we have a vector s, so that the following holds. We start with our solution x in the kth step, and from x, which is our previous solution. So this is the function value in our previous solution. Let's say this is in the k step. We then are trying to improve on our solution xk by adding alpha times s. S is a vector, and this is a descent direction, a direction in which we are trying to descend. Let's make a very simple example. Let's say this is the real plane, and we are looking for this point. So we have x1 and x2, and be careful, we are not saying anything about y or f of x1, x2. We simply say, because for this we would need to have a three-dimensional plot. We'll see this later on. But let's just say that this is the point we are looking at. And we are starting out here. This is x in our first solution. This is a vector. Now let's assume we have, let's use a line here. There's a line. Okay. There should be a line somewhere here. Sorry. Maybe I can... I don't know how to use my... Here is a line. Okay. We'll go into this direction. This is the vector S. And if, for example, we say, okay, let's go in this direction, but a little bit longer, then the alpha would be higher. So we're going into this direction. At this point, we would then say, okay, this is x in the second step. A little bit small. Then we use the next vector and different descent direction, and then we're here, and maybe we'll move to here, and then here, and then here. So you can see that in the kth step, we're using the previous found solution, xk minus 1, and we will add 2xk minus 1, alpha sk minus 1, and so on and so on. And we are obviously requiring that the function value, because we are trying to minimize our function, that the function value f at this new point, for example, from here to here to here to here and here and so on, that the function value decreases. So we are minimizing f in every step we are taking. So an alpha should be larger than 0, so we're moving in this direction, otherwise we could also use this vector. So we assume the step length alpha in the direction sk from xk, and we get a minimization of the previous function value f of xk. That's at least what we're trying to achieve. If we now write the function f of x plus alpha times s simply as h as a function of this step length alpha, then we are trying to characterize the descent direction. And this is done by the following. Again, we need the gradient nabla of f of x. The gradient, if you remember, is in a sense just like the first derivative of a real valued function, the gradient vector points to the slope of a function or a real multidimensional real valued function at this point. So what we are requiring is that the descent, if you want to call it this way, of h, when you take the derivative with respect to alpha at point alpha, which is given by the transposed gradient vector times s, this should be smaller than 0. Meaning what? That the direction you're taking, if you take the gradient of h, the direction leads to a minimization of the function. Okay. And if necessary, may be helpful to normalize the descent vector to the length 1. And you can do this by taking the norm of the vector s. So a general optimization algorithm could then proceed as follows. You first have to find a descent direction. In the last slide we've seen we could also have gone this way, or we could have gone this way, and then you get a different descent vector in every step. Then you need to find the step length, the increment alpha. You update the solution and you abort the whole procedure as soon as you have convergence or any abort criterion is fulfilled. So if you, for example, see that could be a worst case scenario, if you're moving something like this, you can see that you're not converging, but you're moving in circles and you're not really able to minimize your function. In this case, you could simply abort the whole function and the optimization. Okay. Now, optimization procedure will not necessarily find a global optimum. We can only hope for a local optimum. With convex problems, we saw that a local optimum is always a global one, and as a rule, optimization problems are usually not convex. So the risk of local minima must always be taken into account when using optimization algorithms. Same actually in our example later on with interest rates and portfolio optimization. What you can do is, and what is done when mathematicians develop new optimization tools and new methods, what they do is they use test functions. Those are pathologically difficult and complicated functions that are really hard to maximize or minimize. And these test functions, and we'll see a couple of plots on the next slides, you will immediately understand why, if an optimization algorithm is really able to find the global minima and the global minimum of these functions, then it's a really good one. And with the help of these test functions, you can then examine how well the optimization algorithm works. For example, the Ackley function, n-dimensional, and you can see it's okay, it's not too complicated, it's a little bit tricky. We have the exponential function here, we have pi and cosinus. It has a global minimum at 0 and numerous local minima. The bird function is also not too complicated in 2 dimensions, sinus, exponential function, and so on. The Booth function is actually quite simple, x1 plus 2x2 minus 7 squared plus and so on. It has a global minimum in 1, 3 and numerous local minima. The Schwefel function, also minus xi sinus and then the square root of the absolute value of xi. This is what makes it tricky. Again, 1 global minimum and several local minima. And this is the Ackley function. You can see this is plotted in 2 dimensions. So you have, for example, x1 and x2. It goes, this is where the minimum is. And it has numerous local minima. This is the bird function. Looks quite nice. And you can understand that you have local minima here, 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 and on the other side. This is the Booth function, which is, it looks like it has 1 local minimum, global minimum here. Yes, it does, but it also has local minima, which is quite difficult to see if you plot the function. This is from a different angle, and you can see what I mean. And yet another angle. So this is the Booth function, and my personal favorite, the Schwefel function. As you can see, this is a hell of a function, and later on we'll see that the most prominent example of an unconstrained optimization algorithm is usually gradient descent, which is the method of steepest descent. You can imagine this and think of it in the following. You simply take a ball, you stretch out your hand, you let the ball fall down to the ground, and the ball will, as in physics, go into the direction of the steepest descent. So if you do this now, if you, for example, if you start here, if you take a ball and let it fall down here, it will probably fall down in this local minimum. So there's no way, for example, a gradient-based method will find the global optimum, if not by chance. So this is a problem here with the Schwefel function. So let's start out with these gradient-based methods. Very simple. The function f decreases most quickly and most steeply from point x starting in the direction of its negative gradient. If you take the gradient, then it's negative, then the negative gradient should be the direction of steepest descent. So this is why this gradient-based method is also called the method of the steepest descent. The step direction we are taking is minus the gradient at the previous solution divided by the norm of the gradient, meaning what? We are normalizing it to length 1, and then the step length alpha is selected by solving a one-dimensional optimization problem. We are simply looking for the alpha larger or equal to 0 that minimizes this function h of alpha, which is just f of x k plus alpha sk. So we have two actually a one-dimensional optimization problem within this multidimensional problem, and this is the gradient method. So if we are using as an iteration x k plus 1, the solution in the k plus 1 step, equal to the previous solution minus alpha times the gradient normalized. This will give you the gradient method, Gradientenabstiegsmethode, and it converges comparatively slow and relatively poorly near local minima, but we only need the gradient. So we only need the first partial derivatives of the function f, and we are done. Now, the gradient-based methods, obviously the methods has the disadvantage that it can, at least theoretically, only be applied to functions that are differentiable. If you have a function that is not differentiable, you can, of course, you can try to approximate the first derivative, the gradient, but still you need differentiability. Otherwise, theoretically, you have a problem. Now, in the vicinity of the desired optimum, convergence speed deteriorates, and what we have is zigzagging. I actually showed this on one of the previous slides. Actually, if we go back, if you have something like this, this is called zigzagging because you are not really converging, but you are zigzagging around the optimum. So you want to prevent this from happening. And more formally, the comparatively poor convergence of the gradient-based methods is due to the fact that this is a local approximation of the first order. In many cases, the use of a method based on approximations of the second order makes sense. And if you study mathematics or economathematics, this is related to Taylor's rule. We have the function f. Ideally, we would use a Taylor approximation of a much higher order, but if you only take the first derivative, if you only take the gradient, then this is a very coarse approximation, and obviously approximations that use higher order derivatives is better. So the next example is Newton's method, which uses not only the first partial derivative, but also the second one. So this is a Taylor approximation of the second order, and we are now using the gradient, but also information on the curvature of the target function. So as an alternative to the gradient method, we are approximating the target function f of x plus delta by f of x plus the gradient times this delta plus half delta times the Hess matrix, again times delta. So if the Hess matrix is positive definite, so that is symmetrical, and if x times h times x is larger than 0 for all non-zero vectors, then f is locally strictly convex, and if you minimize the Taylor approximation of f, it returns a minimum of f. So this is equivalent to using the Newton-Raphson method on the necessary condition that the gradient needs to be 0. In one dimension, this all boils down to the methods you know from high school, but this is a multidimensional, multivariate extension. So the Newton method is given by new solution x of k plus 1 equals x of k, previous solution, minus alpha, times the inverse of the Hess matrix at this solution xk times the gradient. The convergence speed is higher, it's quadratic, but you need to evaluate more function values. You need to calculate more function values because you have these in the gradient method, but you now additionally need, in every step, in every iteration, you need to evaluate the Hess matrix. Now remember, the speed of the algorithm comes from two parts. First of all, how many iterations do we need? So how should k be? How high should k be until convergence? And how much time does the computer need in every step of our iterative sequence to calculate all these function values? But usually the Newton method should be quicker. So that's the Newton method. Next, let's have a look at some derivative-free methods, because again, if the function is not differentiable, or if you have a hard time calculating the first derivatives, the gradient and the Hess matrix, then you have a problem. So gradient and the Newton method obviously have the disadvantage that they can only be applied to differentiable functions, and you need first and second derivatives. However, a function might not be differentiable, or it might not be explicitly given. This is, for example, the case when f is only implicitly described by simulated data. You only have data and you don't have the function itself. So what to do? In this case, one can resort to derivative-free methods, and, for example, the simplex algorithm according to Nelder-Mead, or simply the Nelder-Mead algorithm. And the idea is, it's a heuristic to evaluate the target function at n+1 different points, exclude the worst value, because at this point f is maximal, replace it with a new value, and if the new point is, if it's better, then include it. If it's not better, exclude this one as well. And the new point is then determined by mirroring this point at the center of gravity of the simplex of the remaining points. You might know this, the simplex is a convex polyeder. Hmm? Okay, so the idea is shown in the following. So we have x1, x2, and x3. Now imagine that x3 is to be excluded, and let this be the point of gravity of this triangle. Then we are taking out x3, we are mirroring it to this point, and then at this point would be our new point x, let's call it x4, and then we would have x1, x2, and x4. We evaluate the function f at these 3 points, see if x4 is a better solution, and then we continue to do this, and so on and so on. This is how it works. Now this is the algorithm more formally. We have n+1 values, xi, in the kth iteration. We determine the corresponding function values and we sort them by size. So this is actually our best solution, and this is our worst solution. Now we calculate the point x0 as the center of gravity of those points from 1 until xn, leaving out xn+1. So, for example, in one dimension, we have simply the average of those previous points. Okay. Now, we calculate the mirrored point. We take the best solution, x0, plus alpha times x0 minus xn+1. If this mirrored point returns a better function value, then we replace it and we go to step 1. If the new point is the best value so far, we calculate the expanded point, which simply means what? If we see x4 is actually the best point, well, then let's continue to do this. We not only use x4, but we use an extended point. Let's go to this point here. A little bit larger. Okay. I'm sorry. Even more x's. So this would be the extended point. And replace the worst point either by the extended or the reflected point, whichever gives you a better value. Go to step 1. And at this point we have the function value of the mirrored point should be larger or equal to f of xn. Thus we calculate the contracted point. We don't expand it, but we go back a little bit. Again, check, is this point better than the worst point? If yes, replace, otherwise do the next. And we replace the n worst values and so on and so on. And you see you have a parameter rho, you have a parameter sigma. This is an example of a very tuned algorithm where you have several steps where you basically are repeating the same idea. You replace the worst point by somehow calculating a point that might be better, and if it's better, replace it. If not, go back. So this is the Nelder-Mead algorithm. These are some default values for the parameters alpha, gamma, rho, and sigma. And let's have a look at this in Matlab. Now we consider a very simple function. we try to minimize the function x1 minus 2 taken to the fourth power plus x1 minus 2x2 squared. Obviously, solution is at 2, 1, which gives you 0 as the global optimum. The function is always non-negative, and thus 0 is the global optimum. Now let's have a look at the gradient. The gradient is simply the vector of the first partial derivatives. If you insert the global optimum, you can see that the gradient at this point is 0. Yeah? First derivatives are 0 at the optimum. And you can use both the functions fmin search, which is a variant of the simplex algorithm, or fmin unc, which includes many various algorithms, which will be switched on and switched off depending on the function you're trying to minimize. So let's have a look at this. Let's first use fmin search. Fmin search, we start at 0, 0, and we get 2 and 1. Again, you can see that at the 15th, 16th decimal, you will have a slight rounding error. And the answer for f of x is 2.9 times 10 taken to the power of minus 17. So it's very, very close to 0, is acceptable. If we are using fmin unc, you can see we start at 0, 0. It will use a gradient-based method, but it will actually yield a slightly worse result, and it will lose approximately 10 decimal places in accuracy. Why? Because it will use an approximation to the gradient, and the approximation is not very good, as you can see. So fmin unc gives us not actually a slightly worse, but a pretty worse result than fmin search. And the reason is the target function around the global optimum is relatively flat. And this is where the approximation, the numerical approximation of the gradient done by Matlab as part of this optimization program is not very good. So if we look at the algorithm, it says by default fmin unc chooses the large-scale algorithm if you supplies, this is a typo in the documentation, if you supply the gradient in fun, and this algorithm is a subspace truss region method and is based on the interior reflective version of the Newton method. If we now change it, one can also use the BFGS quasi-Newton method, which is better. So let's do this and actually supply the gradient. We do have the analytical gradient here. So let's supply Matlab with the with the analytical gradient. At this point, you can see quite nicely, Matlab, at least in this setting, doesn't perform symbolic computation. Even though the function f is very, very simple, and even you can calculate the analytical gradient on paper, Matlab will not do it. It will automatically use a numerical approximation. So if we have the gradient, let's supply Matlab with a gradient. So grad f is a function, this function handler, for x1 minus 2 taken to the third power plus 2, and so on and so on. And we are supplying fmin unc with f and the gradient of f. And as you can see, immediately we get almost 7 decimal places more in accuracy. So supplying the gradient, the analytical gradient, gives you a much more accurate result than simply relying on Matlab's standard default method of numerically approximating the gradient. Now, if you do an error, if actually we get the derivative check option here, what we can do is, unfortunately there's a typo here in LaTeX, should simply be 6 times x1. So instead of saying 4 times x1, we are saying 6 times x1. So we have a slight error, and we weren't able to calculate the first derivative with respect to x1. So we made a small error in the gradient, and let's see what happens. And we turn the option derivative check on. What Matlab will now do is, it will compare the numerical approximation with the gradient we've supplied. And as you can see, derivatives do not match within tolerance. Derivative from finite difference calculation, minus 31,0. The user supplied derivative is minus 48, and there's a difference because the first derivative is wrong. So Matlab sees, yes, there is a discrepancy, and there seems to be an error in the gradient we've supplied Matlab with. So, not surprisingly, the result is x 1.98, 0.992, and we get a slightly worse result. Okay, so that's optimization, unconstrained optimization in Matlab. Now let's turn now to optimization under constraints, and we'll use some penalty function approaches. Now in the following, we want to discuss procedures for optimization under constraints. And we consider a very simple general optimization problem. We want to minimize f of x subject to two types of constraints. The first one, h1, h2, h3, hi in general, is constraints in the form of equations. Gi, g1, g2, g3, etc. Those are constraints in the form of inequations. Nebenbedingungen in Gleichungs- und Ungleichungsform. We assume that the corresponding target functions have the required differentiability properties, and the stationarity of the target function, that is, that the derivative or the gradient is equal to 0, derivative, still some typos here, is equal to 0 is no longer a necessary condition. Why? Imagine it like this. You have a function that looks like this. And we all know a local minimum and a local maximum will be here and here. And why is that? Because in high school we've learned that we are looking for the points where the tangent to the function, okay, sorry, this is not the best line. The tangent in this point is 0, meaning what? The first derivative needs to be 0. Problem is, if we now say we have some constraints, then maybe we're only looking at this part of the function. So this would lead to the minimum, the local minimum being here, and the local maximum here, and local minimum being here, which incidentally would also be the global maxima and minima. Problem is, at these points where we are actually reaching the boundary of the solution space, actually the first derivative will not be 0. You can see this here. So the derivative, the simple rule we know from high school, but also from the gradient methods, gradient-based methods, that the stationarity of the target function is no longer a necessary condition. Could be that the gradient is not the 0 vector, or that the first derivative is non-zero, and still we are looking for a local or global maxima or minima. Ja? Ich sage das vielleicht nochmal kurz auf Deutsch. Bei der Optimierung unter Nebenbedingungen haben wir ein ganz anderes Problem. Ohne Nebenbedingungen können Sie im Grunde genommen wie im Abitur in der Schule einfach immer sagen, ich rechne die erste Ableitung aus, setze die erste Ableitung gleich 0. Im Multivariatenfall arbeiten Sie mit der Hesse-Matrix, mit dem Gradienten, aber letztlich ist immer die Anforderung, die Ableitung oder die ersten Ableitungen, partiellen Ableitungen sind 0, und das ist eine notwendige Voraussetzung dafür, dass wir ein Optimum finden. Problem jetzt hier ist, wenn wir natürlich Nebenbedingungen haben, also letztlich das Ganze nur zwischen den beiden, also wenn wir sagen x soll zwischen 1 und 2 liegen oder so, dann kann es sein, dass wir das Optimum am Rand des Lösungsraumes finden. Nicht dann, wenn wir eine Nebenbedingung erreichen. Und dann ist die Anforderung, dass die erste Ableitung gleich 0 sein muss, die ist nicht mehr notwendig. Es kann auch sein, dass in dem lokalen Optimum, dass die Ableitung ungleich 0 ist. Und das ist ein Problem. Was wir also machen, let's go back to English. So what we need to do is we can use a penalty function approach, which looks at the function f, and it penalizes any violation of any constraint. Okay, another procedure would be to derive other optimality conditions, which most famously are the Karush-Kuhn-Tucker conditions, the KKT conditions. We'll not discuss this in detail here, but I think the penalty function approach is very, very intuitive. So, this is still in German, sorry. The penalty function approach aims at loosening the constraints by incorporating it into the target function and then penalizing any violation of the constraints. So we transform this problem here into an unlimited, unconstrained optimization. This should be unconstrained. Optimization problem with the following objective. Target function. We minimize phi of x, and now we have sigma. And phi is defined as f of x plus sigma times the sum over the squared values of all constraints x1, x2, x3. Why is that? If all those constraints are fulfilled, this sum would be 0. Look at this. All the constraints need to be 0. However, if we have a slight deviation, if any one of these constraints is violated, then by squaring it, you get a positive number, and sigma is the parameter that governs how much this violation of the ith constraint, how much this is penalized and punished. So the parameter sigma can be used to force the algorithm to go back into the permissible solution space. And similarly, you can also do optimization problem with the constraints that can be transformed from inequalities, inequations. You can also say, okay, minimize phi of x and sigma, defined as the target function plus sigma plus the positive part of hi. So we are only using a violation if you're going above 0 and not below. Or you can also square this. And all these approaches are so-called exterior penalty function. Why? Because you are coming from outside the solution space, and by using the penalty parameter, you're forcing the algorithm to move into the direction of this permissible solution space. Now, if the optimum, if it lies on the edge of the permissible solution space, and this is usually the case, at least at one constraint is binding, then the exterior penalty function approach, the optimal, it's not optional, the optimal, sorry, a lot of typos today, the optimal solution is only achieved within the limit value. And if this is undesirable, you can also use an interior penalty function approach. What is done in this case? With these, you have a suitable threshold function, also called a barrier function, and this one strives towards infinity if x from within the admissible solution space strives towards its edge. To see this, we're using this example here. We have again those constraints gi. We are defining the function b as the sum of 1 over gi, and then we optimize by minimizing f of x plus sigma times this penalty function, but not for increasing values of sigma, but now for decreasing values of sigma. So let's see how this is done in Matlab. We are looking at the function x minus 1.5 squared plus y minus 0.5 squared, and under the conditions that x and y are both below 1. Now, an optional, I don't know how we got in optimal. Now, the optimal solution is given by x star 1, 0.5. And an interior penalty function could, for example, be, now this is f, obviously, this is f of x and y, plus sigma times 1 over 1 minus x plus sigma times 1 over 1 minus y. And let's look at this in Matlab. We define f, and we're using a meshed grid to plot this, and we are plotting the contour plot of f for different values of the parameters. So you can see we start out at 0.1, 0.01, 0.001, 0.0001. And what happens is, remember, that the optimal point is 0.5. So actually it is always 1, 0.5. It's here, 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 and here. And we're moving in this direction. And as you can see, if we start out with a very low, very high parameter, a violation of those constraints is not violated too much. And for example, we would be here, and this would be our optimal. Then in the next step, we would be here. And the third step will probably be here, and in the last step, we'll probably be here. So as you can see, we're moving into the direction of the optimal, but from within the admissible space. Okay, so we are, in every iteration, we are tightening the penalty function. So it's very, very simple. However, especially with the exterior penalty functions, some numerical problems can occur, which complicate the application of these methods. And the approaches with penalty functions should therefore be only used as a starting point, and this is the KKT approach, not CCT approach. So the Karush-Kuhn-Tucker. We're not looking at this here. Actually, we had this in the lecture earlier, but this is gone now. So let's rather have a look at the optimization under constraints in Matlab. So we're using linproc, quadproc, and fmin-con. Linproc is for linear functions, linear programming. Quadproc is for a quadratic optimization problem. And fmin-con is simply the generic optimizer in Matlab. So we start with a linear program x1 plus x2 under the condition, the constraint x1 plus x2 has to be smaller or equal than 1, and x1 and x2 should be non-negative. The program now possesses two basis solutions, 1, 0 and 0, 1, and between these two, every convex combination is optimal. So we have an infinite number of solutions, and we now call the Matlab program an algorithm linproc. We have to supply f, a, b, a for equations, b for equations, the lower bounds, the upper bounds, and the starting value. And so we're doing this linproc -1, -1, 1, 1, 1, and the rest is 0. And what we can see is we get as an optimal solution 0.5, 0.5. This is not one of those basis solutions, but it's obviously between the two. So we have one solution here, we have one solution here, and Matlab gives us 0.5, 0.5. It's okay, but Matlab does not see that actually we have an infinite number of solutions, and this is not the unique solution. That's the only problem. Okay, so if we use a different algorithm, if we set the options a little bit differently, we get 1, 0. But there is no difference between those two solutions, obviously, because they are all optimal. Now let's use fmin-con. We minimize a more complicated function, exponential function of x1, and so on, under several constraints. And the function call of fmin-con is function f, starting vector x0, and then a, b equations, lower bounds, upper bounds, and so on. And for the objective function. And then let's use this in Matlab. So we first set the nonlinear constraints, the inequations and the equations, And then function fval is the objective function, exponential function of x1, and so on and so on. We have to define this. And now let's use fmin_con. We have our objective function x0 and our constraints, and we get value 10.5523, 0.9477, and the function value, which is considerably high, but this is the result of our optimization here in Matlab. Okay. So very simple, fmin_unc for optimization without constraints, and fmin_con for generic optimization with constraints. It's only a question how to define those constraints. And then now for the remainder of the lesson, let's have a look at portfolio optimization in practice. So we are looking at the n-security case. We have mu, the vector of expected returns, sigma, the vector of standard deviations. C is the symmetrical n times n covariance matrix for those n securities. W is our vector of portfolio weights, and a portfolio weight of Wi below 0 would correspond to short selling. Now, with fixed weight, the expected portfolio return is mu p bar and sigma squared p bar. Again, you remember this, you simply need to calculate the expected value and the variance-covariance matrix of a linear function in several random variables. So the weight vector that satisfies the Markowitz efficiency must now be determined. So we are minimizing first our portfolio variance under the constraint that the portfolio mean return is fixed and that actually the weight vector adds to 1. Now with the Lagrangian approach, you get this function here, you include it in our target function, and we need to minimize this. Das ist also ein klassischer Lagrange'scher Ansatz. Sie nehmen einfach hier Nebenbedingungen, fügen die mit Lagrange-Variablen in die Funktion f hinzu und dann wird das Ganze minimiert. Now to solve this, we need to set the first derivatives to 0. And if we solve for the weights, this yields this expression. Using both constraints, we get this. Let's call this A, B, B, and D. We don't need to do this in detail. This is simple algebra. And we get a system of linear equations. And this is A, B, B, D times nu and lambda. Those are the Lagrange factors. Equals the weights and the vector of portfolio mean returns. And then we get as a solution nu and lambda equal to these expressions. Okay, now in the very special case that A and B equals 0, the portfolio variance is minimized and we get the minimum variance portfolio. If we now simplify equation 2, we get the weight vector for the minimum variance portfolio. We've already seen in graphics, this is the minimum variance portfolio, and then we have the axial. Okay, so we have the weights for the minimum variance portfolio. What to do next? If we now include this into the formula of the portfolio variance and the portfolio return, this finally yields the return and variance of the minimum variance portfolio. So we know where to put the minimum variance portfolio. And now we are interested in not only the minimum variance portfolio, but in the axial itself, the efficient edge, the efficient frontier. So we insert lambda, nu, and the expected return and the variance of the minimum variance portfolio into equation 1. And this leads to the equation of the risk efficient of the Pareto efficient portfolios. So all these portfolios on the efficient edge. This is the mu, the expected return of the minimum variance portfolio, plus or minus this square root. Okay, so let's take this to the data. We're using the stock prices of 7 DAX companies from 2001 to 2016. Adidas, Deutsche Bank, Deutsche Post, RWE, RWE, Siemens, ThyssenKrupp, and Volkswagen. Source of the data is Yahoo Finance, and those are closing prices from the Frankfurt Stock Exchange, adjusted for dividends and splits. So this is the plot. As you can see here, we have financial crisis. You can see the Volkswagen diesel scandal, and Adidas, Siemens, and Volkswagen clearly outperformed the other stocks most of the time without the diesel scandal, of course. So first we calculate the daily log returns. It's in a vector price. We first get the number of days and the number of stocks in Matlab by taking the size of this matrix price. Then we calculate the log returns, and we do this by first of all defining a matrix return and then going through all those different days, and we calculate the return I is simply the log of price I plus 1 minus the log price of I. And then we multiply this times 100 to get the returns in percent. Now the returns are then cleaned with respect to extreme outliers. We are doing this because we don't want to maximize our portfolio simply and we don't want our portfolio optimization being influenced by extreme outliers, for example, plus minus 20% on one day. We could have left this in, and we don't need to do this, but to give you a better understanding of the optimization, we've cleaned and thrown out those outliers. So you can do this here in Matlab. And at the end, we have 4 days out of 3,722, which were to classify as outliers. Now, next, we calculate the required estimates. So with the expected returns and the variance-covariance matrix and the inverse, simply by taking mean of return, covariance of return, and taking the inverse of C. So we call this C1. Okay. Next, we calculate the parameters A, B, and D. We've seen this here. So you take these equations, actually this one here, A, B, and D. We calculate this before, and then we have A, B, and D. Very simple. Then we can immediately calculate the weights of the minimum variance portfolio. So W var min gives you this vector of weights for those stocks. Problem here is that, actually, let me just see. I think we're not using all those. Actually, no. 2, 4, 6, 7. Yeah, 7 companies, yes. So we should have 7. 2, 4, 6, 7. Yes, 7 weights. As you can see here, the minimum variance portfolio, without having any constraints, the minimum variance portfolio will use short selling. That's why the weights are negative. And then we can calculate the corresponding return and standard deviation for the minimum variance portfolio. And then we calculate the efficient frontier. So we use this mu min plus square root, mu min minus square root, and so on. And then we can plot this. And this is the efficient line and the eggshell, and obviously in blue you have here the minimum variance portfolio, and you get the efficient frontier starting at the minimum variance portfolio. So this is done based on market data and not just simulated data. Now we calculate 2,000 random portfolios by calculating 2,000 random portfolio weight vectors. So this is what we do here. Simply use those portfolio weights and then make sure that they all sum up to 1. And we simulate the portfolio returns. We calculate the daily portfolio returns and take the mean and standard deviation. And we include those random portfolios, which could be naive diversification in a sense. And we plot it in our plot here, in our graph. And as you can see, if you were to simply use random portfolio weights, you would do a bad job. Even this doesn't include naive diversification, but as you can see, for example, you could have taken this portfolio here, you could have done much better simply by trying to get to the efficient frontier. So random portfolio weights are not good. They will give you a risk-return profile that is not efficient. Not surprisingly. Next. Question is, why are the random portfolios so inefficient? Has to do with this here. We're taking rand 1, and it's a random number between 1 and 0. So what actually happens is the efficient frontier of Markowitz's portfolio theory allows for short selling. The weights of the minimum variance portfolio are also negative, but the way we've calculated and simulated those random portfolios, they didn't allow for short selling. Thus, we also have very inefficient stocks and inefficient portfolios in our random portfolio weights. Now, again, remember, we have different degrees of risk aversion, and to the extent to which the investor is risk averse, this needs to be known in order to find the optimal portfolio if we don't have a risk-free investment. Now, there is no portfolio that is optimal for every investor, but every portfolio on the efficient frontier can be optimal for any given risk aversion. Now, each investor prefers a different amount of risk. Therefore, the optimal portfolio is only optimal for a given investor with a specific utility function. So we need that. So in order to do this next, we are using this utility function, mean return of the portfolio minus 1/50 times the variance of the portfolio. So we have risk aversion here, and we now have to maximize this utility function. We look for the maximum utility. We do this by using fmin_con, and we minimize fmin_con, or we are using fmin_con to minimize, so we have to switch this function, our utility function. This is the objective function at x minus and so on and so on. This is very simple. And then we have to require a constraint. The weights of the stocks must add to 1, and without short selling, they all have to be non-negative. So we also need a starting point. And if we now do this, starting value, constraints, no inequations, the stock weights add to 1, short selling is not allowed, and no upper bound on the variables, then we actually can use this fmin_con function for generic constraint optimization to maximize our utility function. As you can see, we get this weight vector. This is in two cases actually. It wants to go into short selling, but this is actually close to 0, and the value is 0.0016. That's the utility, which cannot be interpreted. But we can calculate the mean return and the standard deviation, which is almost close to 5% and 1.6 as sigma. Okay. Now the optimal portfolio lies not necessarily on the edge, but on a preference function from the set in the mu sigma plot. And the preference function is a set in the plot as different functions result for different values of phi. Now, if we now insert the value of the utility function for the optimal stock combination, this will yield the preference function for the value minus phi val OL. So the optimal portfolio lies on this preference function, and this is I guess more intuitive. What we get is indifference curves. You know this. We have indifference curves, and what we need to do is we need to move this out, and then we get, for example, the optimal portfolio here. Okay. Now, why does the optimal portfolio not lie on the efficient portfolio? Now, the efficient frontier of Markowitz allows for short selling. Again, we didn't allow short selling. We restricted them. For example, just like the SEC did in the financial crisis. Now, this constraint of no short selling leads to an inefficient result. That is why we are here. and not maybe on this function here, where we have the tangent of the preference function with the efficient frontier. Now, if we allow short selling, if we leave out the short selling constraint, see what happens now. We are moving to a higher preference function, to a higher indifference curve, and thus we get this point here. So this is actually very nice. We get the tangent point between the efficient frontier and our preference function, the indifference curve. Perfect. Now, next example. Let's continue this. As we can see from this optimization here, including a short selling ban leads to an inefficient result. So we have a market friction, and this creates inefficiencies in the market because portfolio investors would like to use short selling as well. Okay, so this is portfolio optimization done with a preference function. You can, of course, also use different preference functions, different utility functions. Then you might have situations that look like this. Then you would have to move the indifference curves out and until you get maybe this tangent point. Then you would have the optimal portfolio here. Okay, so that's the portfolio optimization in practice here. I would say we've done enough for today. We're very good on schedule, so let's stop here. And if you have any questions, I'm happy to answer your questions right after having stopped the recording. So thank you very much for your attention, and see you next week. Thank you.